So last time, remind me, where did we stop? We went through the main C++ program structure, and then we wrote this example together. We went through, well, here I can go full screen. We went through, well, what are the differences between C++ and C? What are we going to learn or we add to our knowledge that C does not support? And we started by a very simple example of references versus pointers, right? And then we stopped here. Good. So again, some of the basics before we jump into object-oriented programming. The good thing again about C++, it's mostly C under the hood. So variables are almost exactly the same, right? So defining an end variable here, let me find my pen. Defining an end variable here, well, that's in one side, well, that's C out, that's C, and both are C plus, but they are mostly C. As you can see, I define the end exactly the same way. All the expressions on variables are the same. Here I'm using C out compared to printf or scanf for Cn, but that's the only difference. Variables are exactly the same. Yesterday, to be able to use C out, we had this std and then ... like that. C out thing. People asked about this, and I told you, well, later on, in fact, we can get rid of this by adding a using namespace, right? In C++, in addition to classes, there is this concept of namespaces that you want to contain classes and variables that get recognized during certain namespaces, right? Cout and Cin are inside the standard std namespace. So if you just write using namespace std and you include IOStream, you can just use cout directly without needing to add anything before it. In fact, I would say at the very least, for any program you would write, maybe you just add these two at the beginning, right? That's a default thing. Good. Yes, Abdul Nasser from yesterday, Cin is like scanf and cout is the replacement of printf. That's correct. Good. Well, again, basic operations are exactly the same, greater than, like checking equality, checking non-equality, and or even the logical operators, all are exactly the same. So no difference here, right? Maybe the only difference is C++ can have a Boolean type that C didn't have, right? And that's something that well, it's an extension for C++. So here, if you remember from C, what we were saying is that assume, for example, if X, well, let's, well, I have the value of X here. Let's see what is the value of X. Oh, come on. We should have some value of X and Y here to be able to calculate these expressions. Let's come up with a value, okay? So Y is larger than 0 and X is larger than Y. So we should come up with a value like, let's say, 4 and 2. Let's see if that works. So X is larger than 2. Well, that's true because X is 4. That's not, which means not true, so it gives you false, right? If you remember in C, we said this, the result of this is an, well, do you remember what would be the result and the result type of this expression in C? This might be another bonus mark. It's 0 and the type is int. Yeah, thanks. So well, two different persons answered like the two parts of the question, but I would say maybe both of you just send your name to the main TA. So the logical expressions in C evaluate to int because a Boolean is really an int type, and it gives you 0 if it's false and 1 if it's true, correct? While in C++ we have the bool type, so you can have false and true, etc., right? And then you deal with and or exactly the same way. No new information here, so we can quickly skip that. And then if and else, exactly same syntax. You can have if else if, or if else else, written exactly the same way. Good. An example here would be, well, let's assume x is 6, y is 2. We say, well, if x is larger than y, you see out something, x is greater, else y is greater, and else they are equal, right? So it's a very, very naive example. Well, now you are experts, but it shows you how you can use the if else in C++. If you take this program exactly, maybe without cout and IOStream and the std, just like the program with defining the two variables and the if conditions, and you run it in C, it would run exactly the same way, right? So it's exactly same syntax, right? And again, nested ifs, all the rules we have applied in C applies to C++. So no new information as well here. Good. Switch case, although we didn't, well, we covered switch, but not in a very, I would say, detailed hand-on examples in C, but again, they work the same way in C++. You switch on an expression and the case gives you different cases. So if one of the cases is true, you execute the statements of this case and, well, you break, right? And then at the end, you have a default statement, right? So again, same syntax as C. It's a pure revision, no new information. If we looked at an example here, well, we switch over X. We say, well, if X is 1, you see out X is 1, and then you break. This break is very important because you don't want to execute what comes after if they apply, right? And then, well, if you remember from C, do you remember from C if I have this kind of, well, a case with no expression followed by another case, what would happen? What do you think? Well, it might be very clear from the C out statement, but let's see if you remember. If I concatenated multiple cases without statements between them in C, what would happen? Same entry, runs case 3. Yeah, well, it basically runs, well, it says that this statement should really execute if any of these cases is true, right? So it's like ORing, right? So it's basically saying this is why we have the written statement as X is 2 or 3, right? Excuse me, because if you have multiple cases back to back and then you have one statement, it's like if you imagine it in F, you'd say if X is 2 or X is 3 or, right? So concatenating cases is like ORing in F. Good. And then this was the conditional expressions. These are loop expressions, do while and for. Again, no change, all is the same. Well, an example here for a while loop, again, I define a variable, I put a condition, and, well, I increment my variable and just a print X every time. This will print X from 0 to 9, right? Then for for, well, the same thing. And remember from C we said, and maybe you already know this from Python as well, is that for and while are functionally equivalent. Any code that you can write in for, you can exactly write in while by tweaking, right? So they don't add additional functionality. They are just maybe better readable in under certain use cases. So for some use cases, for is better. Usually if you have like large number of iterations and they are consistent, right? So you know as the number of iterations beforehand, while is better if you have a condition that you need to check every time, right? Here it shows you, well, an example for while and then how we translate this to a for, right? Again, we are having a loop of 10 variables. This is the same example we had in the previous slide for while. Here we transform it to for, right? Written exactly the same way, no change, good, compared to C. And then, well, I can also have nested loops, loops inside loops, no change, the same thing, right? So all of this, as you can see, every basic operation, loops, conditional statements, variables, or expressions are exactly inherited from C. So no change, right? Okay, so let me then switch to what we have for today. Okay, so, well, this lecture then is, well, we covered the basics. If you think of what our story in C, we covered basics and then arrays a little bit and then functions and then pointers, strings, right? And then we combined all of this. The same thing here. We did all the revision of the basics. Now we will look into functions, right? In C++. The general rule in function C++, again, everything applies from C, but with certain, well, small changes as we will see them, right? So here I'm just kind of arguing again from the philosophy point of view, our functions are really very useful. The general concept of code reuse, right, which we covered when we talked about functions in C. Assume, for example, I want to write a code that does the simple exponential of like 3 to the power 4. If I do this, then, well, I would just do this code and I calculate 3 to the power 4. Well, later on, what if I want also to add a piece of code? Just make sure I can mute everyone. Just afraid Okay, so I muted myself, but then I'm back. Okay, so and then assume we also want to write, well, the code that calculates 6 to the power 5. Well, I would also write it, right? And then what if I want something else, another number, I don't know, 12 to the power 10? Well, I will write the same thing. If you look here, well, the structure of the code is exactly the same, right? What I do is I keep just multiplying 3 to itself 4 times, 6 to itself 5 times, 12 to itself 10 times, right? So the logic is the same, but the numbers are different, right? So if I keep doing this for every specific use case or input case, and I write hard coded, this is usually referred to as hard coding, this is not a good coding style because your program is not general enough. What you will need to do is simply just write a function that takes these two numbers and calculates the power, right? And in that case, first of all, it's much better readable, right? So it improves readability. If I say, for example, square root of 5 or, well, power 3 to the 4, then it will be much better readable from that sense. It's abstracted, but also it's much easier to maintain, right? Because right now, well, the code is very hard to read. If I want to make a change, I would have to apply it for all the cases. But if you write a function, one single point of logic, if you want to modify it or extend it, well, it's much easier, right? And then at the end, code reuse, right? Code reuse is you can give your code to someone else. You can embed this function in a header file, give it to someone to use. But if you write such code, well, assume your friend told you, you know what, I want to calculate 13 to the power 14, right? Well, you cannot share your code with him at all unless you give him the source code, he modifies, and then to come up with his own version, right? But if you wrote the function, you just give him the function. Yeah, I say, I have a function that calculates this, embed it in a header file, he can just use, right? So code reuse and code sharing and abstraction is very important in that concept. And in fact, functions, I would say, is the very first step towards this general concept of encapsulation, object-oriented programming in general, right? So this is basically the function that does the three previous examples. We maybe call it raised to power. We have a base and we have exponent, and we just write this piece of code. If I want to use it later on in the main for the three examples we had, well, single line of code. Every time I just call it, I say raised to power 3 and 4, 6, 5, 12, 10, right? So it just shows you how functions are really, first of all, the code is much more compact, better readable, and reusable. Good. Then, well, some, again, reviews that, again, these are from C, but I'm just reviewing for those that might be confused or don't remember. So simply, you cannot use a function before you define it, right? So if you, for example, you have a main or another function that's called foo that wants to use bar, but then bar is defined afterwards, well, this is not allowed. The reason is, well, bar is not defined here. We know from our first lecture, compiler executes code in a line by line basis, right? So if you do that, and I hit this line, which is return bar multiplied to 2, I don't know what is bar, right? So what can I do is either bring the full definition of the function here, or add the prototype here, or the third method we discussed previously in C is you just add a header file, right? Good. And we said that, well, a function is composed of three things. Well, the prototype or the signature, which is basically just, well, the first line, it tells you what is the return type, what is the name, and what are the input parameters. Here there are no input parameters at all. And then the function body or definition, which includes the implementation. And, well, the third part is the function call, right? This is the function call. Good. So that's the call, that's the definition, and that's the prototype or signature. Good. Okay, and then we said, well, it's much better, and you have seen this in labs already in C, is that, well, you would better organize your code in header files and source files. Header files only includes the function signatures, definitions, right? And source code is the implementation. And the good thing about header files is this is the only thing you need to share with someone to be able to use your source code implementation. So as a user, scanf or printf, we don't know how they are implemented, right? But we are able to use them because we have their signature, right? So that's basically what is in the header file. And we are including in our programs studio.h or iostream .h for C++, and we are able to use them without looking into the source code or including the source code. Good. Then here is one thing that we didn't cover in C. In fact, well, last year I had a separate lecture for recursion because usually I see recursion a lot in coding interviews, and it's a concept that's a good concept anyway. So it helps you solve hard problems in, I would say, a logical mathematical way, right? If we had the time towards the end, I might also dedicate one separate lecture for recursion. I guess it will be very useful. But until then, what you need to understand is recursion is not really a new information about the programming language. It's just a way of using it, right? What is recursion? It's simply using the function inside itself, right? So a function can call itself, and this can happen in C or C++ or any language, in fact. Why this might be useful? It's useful in iterative calculations, right? Assume, for example, you are operating on a database or a graph or a tree, right? And you want to repeat certain operations, right? Find a certain variable, right? And you want to build in your steps one by one, right? This is a typical case for recursion, right? Here I'm showing you a very typical textbook example that everyone, when you talk about recursion, this is the first thing that comes to your mind is the Fibonacci series, right? Because Fibonacci series, if you express it like in a mathematical format, you simply, like the Fibonacci number of n, it's equal to the Fibonacci of n minus 1 plus the Fibonacci of n minus 2, right? Now, if you really want to calculate the Fibonacci of 100, and you have already calculated the Fibonacci of 99 and 98, do you really need to recalculate the Fibonacci of everything for the 100 from 100 to 1? No, right? You can just add these two, right? Which means, generally, for a number n, I can call the function itself. This is the recursion here. I can call the function for the previous two Fibonacci numbers, right? n minus 2 and n minus 1. Good? So this is usually called the step in recursion, right? This is basically the step, the thing that needs to repeat, right? But there is one very important thing in recursion that people usually most of the time don't get, and it causes the problem, which is the base case, right? So simply, where do I stop? I keep recursively calling myself, right? From, for example, 100 to what? 99, 98, etc., etc. But I should stop at a certain point. This is usually referred to as the stop condition or the base case. For Fibonacci, is either the 0 or 1 because, well, Fibonacci is 0 is 1, Fibonacci is 1 is 1, right? So in that case, you would simply return 1. How this is going to work? Let's take this example. I'm really kind of spending more time here in recursion because if we didn't have the time to touch on later, at least you get the general concept. But maybe also I should ask, did you cover recursion in Python in the first year course or no? So you have some familiarity with the concept or no? Yes, no, do remember a little bit?
I think we touched on it.
Okay. Okay, so if you want to understand recursion, you want to see how it executes, right? So take an example. Let's say I want to calculate the Fibonacci of 5, right? In that case, I'm passing 5 to this function. So the first case is it's fib5. The base case does not apply to 5 because it only applies to 0 or 1. So you go to the step. In the step, you call Fibonacci twice, one for fib3 and one for fib4, right? So here, this is basically the recursion. And then by calling fib3, what would happen? You repeat yourself. It's exactly the same thing for fib5. Fib3 would call fib2 and fib1, right? Fib1 is a use case, so you stop here. While fib2 would be really calling fib1 and fib0. But both are base cases again, so you stop here. For fib4, well, you would call fib3 and fib2. Fib3, we already went through the tree. For fib2, well, we already went through the tree as well, right? So you keep really recursively calling yourself each function in instance is a function in the stack on its own, right? Passed in with a different input parameter, it calculates it, it gets back. So what is important here is to understand really how the result propagates back, right? For example, for fib0 or fib1, let's take this path. Until I'm doing all of this, I have no return value, right? Like nothing is returned. I never hit this case here, right? So there is no return, right? But once you hit the base case, you return a value. So for fib1 or fib0, you return 1 here, right? If you return 1, we know from functions that when a function returns, it returns to the line that was directly after the function call in the caller, right? So the compiler executes, I hit a function call, I go execute it. Once I return, I get back again to the same program counter of the original caller, right? So here, once I return 1, I'm returning 1 here, right? But here, so I return 1 and 1, so it's 1 plus 1. So for fib2, the code here will be saying return 1 plus 1. So fib2 will return 2 for you, right? While fib1 will only return 1, right? And then for fib3, well, this line executes. So you have 2 and 1, so you return 2 plus 1, so fib3 will return 3, right? And then you keep doing this, right? So if you want to visualize it, and in fact, there are animations on the internet as well that shows you how they execute. It's very important to understand it, because the thing about recursion is not really in how many lines of code you write, right? It's very, very small here. Recursion is usually a very small piece of code. If it becomes large, then recursion is not the best use case here, right? But the problem is how to formulate it correctly, right? To capture the use case, right? So is there any question, right? One thing also I can do, I can share with you the slides and the video from past year anyway. If we manage to cover, that's good. If we didn't manage to cover, at least you have a reference, and then maybe I can take questions later. Because in fact, I believe recursion is one of the concepts that, well, it's very important for you for programming and internships and interviews, and like even like in your way of thinking generally, right? Good. Is there any question on this kind of abstraction we covered? Okay. So now, well, we have been very boring in the past half an hour. Everything is, well, C, no change, right? So let's look into some of the C++ new stuff. C++ has what we can call a function overloading, right? What we mean by this, in C++, I can define a function. First of all, from C, we mentioned that what defines a function is a signature, right? And what is a signature? Is the return type, the function name, and the input parameters, right? In C, you cannot have two functions with the same name, no matter what, right? While in C++, I can have functions with exactly the same name as far as I change either the return type or the number of input parameters, right? So if there is any change in one of these two, the function can still have exactly the same name, right? Why this might be useful? Because you might want a function to do exactly the same functionality, but in different number of input parameters, right? Here I show you a very simple example. Assume I want to write a function to print something in a new line, right? But this something can be really anything. It can be an int, a double, a character, doesn't really matter, right? So in C++, what you can do, first of all, in C, what you can do is you need to define for everyone a function with a different name, right? So maybe you write something like print on new line int, print in new line string, right? Something of that sort. While in C++, here, the function name is exactly the same, while I'm only changing the input type of the input parameter, right? And this is a completely valid well, piece of code in C++. It's not allowed in C. Then the question is how the compiler, when you call this function, print on new line, how the compiler would know which version of the function you want to call. What do you think? Well, it's already written here. So it's basically the compiler will know from the type you are passing, right? So if I have a main here, for example, I say print on new line and I pass 3, the compiler will figure out the 3 is an immediate integer value, so it will call this version. While if I pass something like print on new line hello, which is a string, then it will call the new one, right? So function overloading, and well, this is the name overloading because you have one function name that does multiple things. The compiler allows you to enables you to dynamically call one of the versions of the functions you have based on what you pass to this function, right? Good. So here we have shown that overloading can be done by changing the input type, for example, from int to a character pointer or a string. It can also be overloading by changing the number of input parameters, right? The first version is taking only a single int variable, while the second one is taking 2, right? And again, how the compiler would know? Well, based on how many input parameters you pass to the function, the compiler will call the correct version, right? Good. NDL, okay, Ahmed, NDL is from yesterday, like where it's like new line basically, right? So it's a reserved word in C that replaces this special character \n, right? Good. So overloading can be done by changing the type or the number of input parameters. Good. Another change in functions that we have seen yesterday when we compared references with pointers is passing by value versus pass by reference, right? In a pass by value, well, it's exactly the same as C. No change at all. I just, well, I define the variable name. Here, for example, I have a function called increment. I'm just adding a equal a plus 1. And what would happen is if I'm really returning nothing, what do you think would be the value of Q here? So if I execute this piece of code, what would be the value of Q? Three. Yeah, Jack, thank you. Because basically A changes here. So A takes 3, and then I increase A from 3 to 4. But A is a local variable in this function. Once the function is being destroyed, I return from the stack, A is lost, right? So Q does not get updated. And if you remember, we had this animation in the function in C that copies the value, but really they are completely decoupled. They don't relate to each other. Q and A don't relate to each other. Separate memory locations, right? This is the pass by value, and this is the same as C. No change here. So that's the animation. So here, that's the main function scope, Q equal 3. That's the increment function scope, A is equal 3 because we copied the value, right? But once you increment A equal 4, Q has no knowledge at all about this. And then once you, destroy, Q remains 3, right? While for passing by reference, the way we have done the passing by reference in C is only through pointers, right? But from yesterday, we kind of learned that there are 2 ways to do this in C++, one through pointer and one through reference, right? So here, you can write this piece of code that takes an address of an int variable. Well, this is a reference, this is not a pointer, right? That's very important. And well, by doing so, if you pass Q here, in fact, in this case, Q will be incremented from 3 to 4, right? So if we have the animation, well, I'm not really passing Q as a value, I'm passing the address of Q. And in this case, A is a clone of Q. Any change to A will reflect to Q. So if I'm updating, well, that's the swap thing. But if I'm updating Q, it will just go to 4, right? That's another example of the swap, right? If I do a function swap, then, well, let's look into the animation, or maybe this is something I can really code with you because that's a concept that is very important. And also we can do this in pointers as well. So let me C++ and then